SIP9 Hub. Welcome to another episode of SIP9 Hub. In this video, we will present to you integration by substitution, or we call it change of variable. But before we continue, do not forget to like this video, hit the subscription and notification bell to stay updated of future videos. Substitution is a way to compress or compact a complex expression by introducing a new variable. By convention, the variable that we introduce is the variable u, and of course this is not a strict choice, so you can introduce a variable of your own preference, but in this presentation we will use this variable. In fact, this is the reason why other authors call this process u substitution, because it's always the variable u that they use. But again, I want to emphasize that there's nothing wrong if you want to use a different variable. We do this, we introduce a new variable, not because we want to change the expression that we are dealing with, but we want to make it simpler for us to deal with them. For example, it makes it easier for us to integrate them. In the last video, if you still remember that, we talked about the different properties of integration, and sometimes these properties are difficult to apply if we do not adjust our integers. There are a few things that we need to remember when we are applying substitution as a strategy in integrating. The first one, we need to make sure that after selecting a part of the integrand as your variable, say u, we need to make sure that the rest of the integrand is substituted with respect to that variable u, or any other variable that you introduced. Say we are to integrate 3x cubed minus 2 raised to 7 x squared dx. Suppose further that we are going to let this part of the integrand be the value of our u, so we are introducing the variable u. Then we need to make sure that we find a substitute for the rest of the integrand, which is x squared dx, and we do that by exploring the derivative of u. So let's go ahead and do that. So we let u equal to 3x cubed minus 2, and the derivative for this is, from our previous presentations, the derivative of this expression is 9x squared. The derivative of negative 2 is of course 0, so the derivative of u with respect to x is just 9x squared. From this equation, we can write du equal to 9x squared dx. But remember that we are only looking for a substitute of x squared dx. So if you notice, that expression is the same as with this one. If we are going to isolate x squared dx from this derivative, then we would write du over 9 equal to x squared dx. And there you have it, your substitute for x squared dx. We now proceed with our substitution process. The original integral can be written as u, that is your u. X squared dx is the same as du over 9, that's raised to 7. That's the original exponent, 7. 1 over 9 is a constant, And by the properties of indefinite integration, we can factor that out. So we write 1/9 integral of u raised to 7 du. We may now proceed applying the power rule for integration, because we can do that. If you notice, our integral now is much simpler, and therefore the properties that we mentioned, the power rule, is much easier to apply. Let's do that. We write 1/9. Applying the power rule, we have u, you add 1 to the exponent, so it becomes 8. And then that becomes a denominator. We are doing indefinite integration still, so we need to add c, the constant c. We can simplify this one as u raised to 8 over 72 plus c. Another point that I want to emphasize here is that whenever we're going to introduce a variable, the final result, the result after integration, should be the original variable x. So we do not stop with this answer u raised to 8 over 72 plus c, but we need to change it back to our original variable, and that is the variable x. We continue our solution as, remember, u is equal to, we set this a while back as 3x cubed minus 2. Therefore, we're going to use that information also to change the variable back to variable x. We will write 3x cubed minus 2 raised to 8 all over 72 plus c. This can be our final answer. Third point that I want to emphasize also is that there is actually no fixed rule in identifying which part of the integrand should be equated to the variable that we are introducing. So you might want to ask me, how did I know that in the integral we just integrated a while back, the part of the integral that I'm going to let as the value of u is this part and not the other part? Well, to answer your question, integration by substitution is actually more of a trial and error process, and I choose this value 3x cubed minus 2 because it makes the integration process simpler and possible, and also it gives us a more simpler and elegant answer. If we let this part as our value of u instead, let's do that. Let's see what happens if we have the value of u equal to x squared instead. From this value of u, if we work with our derivative, then we have du with respect to x equal to 2x. And if we now proceed with our substitution, that is u. The problem here is we do not have something to substitute for the rest of the integral. What should be the value of this quantity if we let u equal to x squared? Our task of integrating this one is much more difficult or even impossible if we do this instead. So when we look at our integral and we are deciding which part of it should be the value of u, we need to think which would make integration possible and easier. Here is our next example. We have 3 times the quantity 3x plus 8 raised to 11. Again, we are applying substitution because expanding this one instead is a much more difficult job to do. Now let us decide which part of the integral should be let as the value of u. I guess there is no debate on whether which part of it should be u, because we can only see this quantity here that should be the value of u. Letting this one instead as the value of u would not help us at all. So let us go ahead and erase that one. The value of u is equal to 3x plus 8. And if that is its value, we need to remember again that we have to look for a substitute for the rest of the integral, that is 3 dx. And we do that again by exploring the derivative of u. What is the derivative of u? Or du with respect to x. Derivative of 3x is just 3. Derivative of positive 8 is just 0. So you only have 3. We can rewrite this one, this equation here, as 3 dx. We can multiply it here, 3 dx. And there we have it. This is exactly the rest of the integral. So we can proceed with our substitution process. We now write integral of, that is u raised to 11 du. We can now use power rule to integrate this one. We proceed writing u raised to 12 over 12 plus c. Again, we need to go back after integrating. We need to go back to our original variable. And that is, what is the value of u? Our value of u is 3x plus 8. Let's go ahead and substitute it back. 3x plus 8 raised to 12 over 12 plus c. There we have it, our final answer. Here is another example. We have a more complex integrand. So our first task is to identify which part of it should be let as the value of u. Should we let the value of u equal to square root of 2x plus 1, or you might want to simply use 2x plus 1 instead. Which is better? Personally, the decision of what should I let as the value of u is dependent on whether which of them can I easily differentiate. Because remember, the next step after identifying the part that is the value of u is to differentiate. If you know how to differentiate this one, then you can proceed doing that. But if you don't, if this is easier for you to differentiate, then we can do that. For now, I am going to take the second value of u, 2x plus 1 only, and not square root of 2x plus 1. Let me erase the first. Let us continue by exploring the derivative of u. The derivative is just 2. The derivative of 2x is 2. The derivative of 1 is 0. Now, remember that we let this part here equal to u. It's the same expression in the denominator, so that the remaining part of the integral is simply dx. This means that we are looking for a substitute for dx. And we can look for a substitute for dx from the derivative of u. Remember, we can write this expression here as du over 2 equal to dx. I'm doing that because I want to isolate dx. We can now proceed writing our new integral as integral of cube root of 1 minus square root of u, this is the variable that we introduced, over still square root of u, and the value for dx is du over 2. This is our integral now. Let us look at this integral, cube root of 1 minus the square root of u all over square root of u. What can we do first? Well, we can factor out again our constant here. We have 1/2. Let's do that. We have 1/2 integral of cube root of 1 minus square root of u over square root of u du. That's because we just factored out 1/2. Now I want you to look at our integral now. Do you think this is simple enough for you to integrate? I mean, to use the properties of indefinite integration that we presented earlier. If the answer is no, then the next step is to further introduce a new variable just to make the integral simpler and easier for us. In fact, we can repeat the process until such time that we are able to easily integrate it. I'm going to introduce a new variable. I'm going to call it v. Now, which part of this integral should we let as the value of v? I will choose this part here, 1 minus square root of u, and differentiating this one, derivative of that variable with respect to u, so we write dv over du is equal to, the derivative of 1 is again 0, so that's negative, and then the derivative of square root of u is, from our previous presentation again, is 1 over 2 square root of u. Remember that we are trying to look for a substitute for du over square root of u. So from this derivative, we need to isolate, if we can, du over square root of u. Let's do that. If I'm going to put du in the numerator, then we would have dv equal to negative du over 2 square root of u. But then again, we are only trying to isolate du over square root of u. So I'm going to put this one, negative 1/2, in the other side. We can finally write it as negative 2 dv equal to du over square root of u. This is the part of the integral that we are looking for, and it's equivalent to negative 2 dv. Let us go back and rewrite our integral. Let us go back and proceed with the second substitution process. This is your original constant, that's 1/2, integral of cube root of, we let this as variable v, and the rest, this one, is just negative 2 dv. Negative 2 is again a constant, so we can factor that out. So we can write 1/2 times negative 2 that's from the inside, we are only left with cube root of v dv. Our constants cancel out and simplified as negative of the integral of cube root of v dv. There we have it, a simpler integral for us to work on. We can apply power rule for this. Let's write it first as v raised to 1/3 dv, and proceeding with integration, we have negative of v, power rule 1/3 plus 1, that is 4/3, all over 4/3 plus c. That means our remaining job here is to simplify this one. We write negative 3/4 integral of v raised to 4/3 plus c. Or we may write negative 3/4. How else can we write this one? That's the same as v cube root of v plus c. Just a quick review in your rules of exponent. V raised to 4/3 is the same as v raised to 3/3 plus 1/3. These are all in the exponent. 3/3 plus 1/3 is the same as 4/3. We can separate this one as v raised to 3/3 times v raised to 1/3, and therefore we have v raised to 3/3 or 1 times v raised to 1/3, and v raised to 1/3 is just the same as cube root of v. That's where we got v cube root of v. Let's go back to our answer. Again, as emphasized a while back, we do not stop with the variable that we introduced. Let us go back with our original variable. And since we applied two substitution process, going back would require two processes also. So first, from variable v, we go back to variable u. Remember that v is equal to 1 minus square root of u. So anything that is v is changed to 1 minus square root of u. So we have negative 3/4. V is 1 minus square root of u, cube root of 1 minus square root of u plus c. And then from variable u, we change it back to our original variable x. Remember again that u is equal to 2x plus 1. Our final answer then is negative 3/4 times 1 minus square root of 2x plus 1 cube root of 1 minus square root of 2x plus 1 plus c. There we have it, our final answer. For other concepts in integration, I will see you in the next video.